And an angle plate goes with the surface plate, which is right here. And this is exactly 90 degrees, exactly. And it's used to, obviously, to hold things at 90 degrees. You'll later on use it to grind things so that it's perpendicular to it. This, as the shape would be known as, is a V block. And it's made for round things. If you have a round pin to put in there, that's how you'd hold it, okay? You would hold it with a V block, okay? That's what V blocks are for, typically speaking. So V blocks are square, just like they are with angle plates. Not only square that way, but they can be square this way as well as they can be squared that way. Okay, they usually come in sets of 2 that are matched together, which are really nice, which we don't have. This is a surface gauge over here, a surface gauge. And a surface gauge is something that you use to check parallelism or flatness. So let's check. How many of you say that this surface here is parallel to the surface down here? Okay, you might say that. Let's check. I don't know. I'm going to put this over here. I'm going to get real close to it. Okay. And I'm going to try to get the needle about as parallel as possible to the surface. I'm going to get it real close, but I'm not going to touch it. Because I got a little knob back here. See that? As soon as I turn the knob, it moves this thing up and down. See that? So I can actually determine how much back pressure I'm going to have on that thing. And as you can see, I put exactly 12 thousandths. And so now I've got 0, and I can just run that bad boy across, and I can check to see if it's parallel. Yeah, run that across like that. I can say, wow, that's really parallel, right? That's one way to use the surface gauge, okay? Height gauge, again, digital and non-digital, okay? Angle plates, surface gauges. Surface gauges also have a little V in the bottom. That's in case if you have something that you want to sit it on that's round, you can do that too. Okay? That's what it's there for. You will also notice that a surface gauge has these little pins behind here. See these little pins? Yeah. And these little pins stick out below it. Here's what that, whoops, shit, almost made that fall. So here's what they're made for. You notice that they stick out and you go up against the surface, so now I can go parallel that surface. See that? Catch that on tape? You didn't catch the bad words, did you? All right. So that's what those are for, those little pins. A lot of people don't know what they're for, but that's what they're for. And they're made also, they got 4 of them, so they can do the sides as well, like this, right? Yeah. So that's kind of cool. All right, so some more stuff. 1 in 10 tool makers know what this is. This is what we call a squareness comparator. Squareness comparator. So let's pretend that this is our master angle plate. That means it's exactly 90 degrees. And this is actually our master over here, angle plate. It's granite, and we know it is exactly, I'm just going to check something real quick here. And I'm just going to put this bad boy up here like that. Make sure we get it up to the top. And I'm just going to move this up a little bit. And you'll notice that this has a ring here, a round ring. See that? And if I push this ring up against there, you got to be very careful with this. If I push that ring up against there, and it's up, it won't go any further, and my indicator's not touching, I can make it touch by just adjusting this a little bit and making it touch and zeroing it out. And then when I go like this, I'll just make it read 0 right now. It'll read 0 right here. Now I want you all to take a look at this. The needle's touching and I'm touching here and it's reading 0 over here. This means that the bottom and the needle are exactly parallel to the angle plate. Exactly parallel to it. And it's square to the surface. Okay? Now the reason it's called a squareness comparator is because I'm going to take something that is a known square, it's known to be square, which I'm going to assume this granite block is square. And at work, you would have something, a calibration sticker that said it was square, it's calibrated, you know? That's what you want. I can tell you it's square, okay? So we'll say it's calibrated, it's square. So we know this is square, this is our standard. But George Bonon made this one here in the shop, and we don't know if it's square or not. We better check his work. Looks square to me. Looks square, right? Let's see how square it is to the master. So I do this, right? And oh. Well, wait a minute, I'm on a hole. I'm on a hole. Oh. It looks like it's about 1/1000 off, okay? 1/1000. Okay? So, again, I would go back and I'd make sure that this was, you know, again, correct. Oh, wait a minute. It wasn't quite adjusted. All right, there we go. Let's check this now. Oh. Look at that. Right on the money. Well, we won't fire him today.
Right.
Okay, because he's okay. He's on the money, right? Okay. Always got to check your work, though. Okay, because sometimes you take a measurement just like on a vise, right? You guys line it. Be careful. What do I say? Wipe that vise, right? You guys start loosening bolts and start making adjustments, but you forgot to wipe the vise, and now it's like, it was a 1/2 thou off, now it's 500,000 off. You know, oh, ugh. But that oil accounted for about a 1/2 thou, right? So, okay, so this is fairly square to this, meaning that I can use this now, okay? All right, so this is a squareness comparator. This is a really neat tool, okay? It's a really neat tool. Not too many people know what this is. I was at a community college, I won't tell you which one, here in the LA area, and the guy asked me to teach a blueprint reading and inspection class. And I went, okay. And I said, where's your inspection equipment at? Well, we got a mic there. Great. I got a mic too. Let's see if they both read the same, right? So I grabbed my little standard over here and I, check his and I check mine. Mine's good and his is not so good. I said, is that the only thing you have? He goes, well, what else do you need? I'm like, well, there's a few things. So I made a list for him, and one of them was a squareness comparator. Now, I was really flabbergasted to find out that the guy did not know what that was.
Was he in the industry too, or just?
And I won't say. But I was really surprised. I was like, you really don't know what a squareness comparator is? Yeah. Never seen one before. Don't even know what the hell it's for.
Sometimes you get those guys.
Yeah.
Just like, nah.
Don't need that. You can see it's square. Right? So, again, level of education. Okay? So I showed him what this is. He goes, God damn, that's pretty cool. Like, okay, cool. So we got that. Now, there's a few other things. There's something called 1, 2, 3 blocks. Now, 1, 2, 3 blocks are like your parallels. Okay, but they're really precise. And the reason they're called 1, 2, 3 block is because they're 1 inch thick, 2 inch high, 3 inches long. 1, 2, 3. And they put holes in them. And they're matched sets. Okay? And they are parallel. They are very parallel. So let's just check them out and see how parallel, right? And let's see if they're the matched set, because I don't know that they're the matched set, to tell you the truth. We got people that donate stuff here and then they get mixed around, but all right, so let's just put a 0 on this bad boy. Very parallel. Let's check this one. And if these are matched sets, then this would be 0 right on the money. Woohoo! It's a matched set. How about that? And that one's 0. Okay, so we're cool. So these two are matched sets. So they're exactly the same height.
Just to be clear, you're saying it's parallel. That surface is parallel to this
Yes.
surface.
Right. I don't know if it's square to that.
Right.
I would have to check with this. So parallel and square, right? And if it's square and it's parallel on this surface here, this is parallel to this. And if this is square to this, okay, if I say this is square to this, and this is parallel to this, then by default, this is square to this, right? Because this is square to this is parallel to this has got to be parallel to that, and squared. And then you would do the same thing for the other side. You check the squareness up against here with this, and then if it's square, like the other one, then you could say this and this are parallel, this is square to this, and it's square to this, and this side is square to this, to this, to this. Now you just got to go like this and establish to see if it's parallel this way. And if this is parallel to this, then it's pretty much square all the way around, with the exception of the ends, which I haven't checked. Right? Okay, so that's how you establish squares. Okay, so we got that. Some more stuff. Sign bar. I think I talked about sign bar. This is a 5-inch sign bar. It's kind of nice. Goes up and down, right? So how do you use it? Well, you use it in conjunction with something called gauge blocks. Gauge blocks? Blocks? They're magic blocks. Magic blocks. Okay. So you do something called ringing the gauge blocks together. This means removing air. You're reading about that. Good. Because if you put two things together like this, you just put them on top of each other. Too much coffee, George. You got, put them on, there's air in between it. Okay? So this is 1 inch and this is 950 or 900. So together they should be 1 inch 900. Now, if you use a ruler and you check it, you'll say, yeah, it's 1 inch 900. But that, we're talking about thousands and millions of an inch. So you have to do something called ringing in the gauge blocks. So you do this, crisscross applesauce. Okay? Crisscross applesauce. Remember that from school? Everybody do crisscross applesauce? Yeah. And you twist it like that. And if you do it right, you remove the air and they stick together. What kind of witchcraft is this, George?
Chris Angel.
Oh, the Antichrist. So now when I put it down on the ground like that, and I put it like that, I will have the exact measurement. So then you go, well, that's great, George. That's really good. And again, you twist it. Now there's another way to remove the air between, and it's called sliding them together like this. And you got to put pretty much pressure on, but it still sticks. See that? Still sticks. Two ways to do it.
Next evolution, keep it playing.
All right. Now, how to use these things? Well, if I need a measurement, a specific measurement, and you have this handout in your training materials under measurement, and it's called, now I say this, this looks like somebody ripped this off. Ah! What the hell? Somebody, yeah, it looks like somebody took my little. There's one of them that says, the handout says how to use gauge blocks. Okay? And it's an old one. It's been around since probably 1960 or so. But it's still applicable because the gauge blocks haven't changed. Okay? So, if I want an angle, I want the exact angle of 30 degrees here, all I have to do is know what the sine of 30 degrees is. Now on your calculators, you would punch in 30 and then push the sine, S-I-N button. And it would pop out with a number called 0.500. Look at that, great, George. Now you're all going to receive, as a special offer today, one of these. Okay? This is called a little Trig Book. And back in the day, you had to be able to use a Trig Book. Well, what's a Trig Book? A Trig Book is going to allow you to figure out angles. It has the 6 natural trig functions from 0 all the way to 90 degrees. Okay? Because when you look at a math diagram, a circle is made up of 90 degrees, 90 degrees, 90 degrees, 90 degrees, right? So it just starts to repeat itself. That's all it does. So all you need to know is the 0 to 90 degrees. So in here, in this little Trig Book, you notice you open it up and it goes, oh, 0's here, that's 0 degrees. And there's 1 degree. And then you go, okay, let's go to 30, George. So you go to 30. And you say, wow, 30. There's the 30 page. See that 30 page over here? That's 30 degrees, right? And then you see this chart, right? You go, oh my gosh, look at all those numbers. Do I have to add all those numbers together? No, you do not. You will notice that over here, there's a little column with the M in it. M. See the M? See the M? M? See the M where my finger is? The little M? Anybody know what that means? Almost. Look at the clock.
Minute.
Minutes. Minutes. Degrees are specified. 1 degree is how many minutes? Anybody?
1 minute.
Well, not 1 minute. How much is 1 hour?
60 minutes.
Very good. 1 hour, 1 degree, okay? So, down here you'll notice the minutes goes all the way down to, holy cow, 60 minutes. Look at that, all the way down. Because you could have 30 degrees, 1 minute, 30 degrees, 2 minutes, 30 degrees, 3 minutes, 30 degrees, 4 minutes, 30 degrees, 5 minutes, 30 degrees, 30 minutes.
Well, do you have to go from degrees to minutes on this class as well, or is that like later on?
Degrees and minutes. A degree is this, a minute is this, okay? So
You
yeah,
had a worksheet that you had to go back and forth between them.
decimal degrees
Yeah.
and
Yeah.
minutes, okay, difference.
Oh,
Okay, decimal degrees is, we'll talk about that later,
All right.
okay? Right now, we're just talking degrees and minutes of degrees, okay?
okay.
So if I look over here and I want 30 degrees, I'm gonna say I want 30 degrees exactly, so that's 30 degrees, no minutes, 30 degrees flat. Okay? And over here on the columns, you'll notice that there's a sine, cosine, tangent, cotangent, secant, cosecant. Sine, cosine, tangent, cotangent, secant, cosecant. I'm interested just in the sine. All right, young man, you got good eyes. What does that read right underneath my thumb? What's that? Point what?
0.50.
0.500, 500. That is the sine for 30 degrees flat. This happens to be 5 inches. From the center of the roller to the center of the roller. Okay? So all you gotta do is multiply 5 times 0.500. So do it in your head and tell me what that number is.
Fine line.
250,000.
Huh? How much? Who can tell me? Come on.
Five times
0.5.
five.
So you grab a 2-inch gauge block,
Oh.
and we grab a 500 thousandths gauge block. And when I ring them together, like so, this will be exactly 2.5. And now this angle magically is exactly 30 degrees. Okay. And if I put something on there, and I try to measure it with this, let's say there's a flat on there, it's the 30 degrees. I can put my indicator on there and check it. See if it's 30 degrees, exactly. Or I could put this in a machine, and I can take an end mill, cut it. Yeah? Or I could put it on a grinder, surface grinder. Questions? Okay, let's do one more, just for fun. You know what angle I'm gonna do too. Huh? I'm gonna do 45. So who can tell me what the sine of 45 is? Two common angles, 30 degrees and 45. Very, very. Who can tell me? Point.
He's just making stuff up. I know, come on.
I got the point right.
Come on, I'm waiting, buddy.
He's doing it for the views.
Good time.
So I'm gonna look down here, and the sign says it's 0.70711, or very close to it. Let's round it off to 0.707, okay? Now here's the way I remember 45 degrees, the sine of 45 degrees. Does everybody remember Air California? No. You remember Air Cal, right? It was a airline at Orange County, based in Orange County, called Air California. And they fly out of Orange County, and they go everywhere in the state. Called Air Cal. So George Vaughn gets on Air Cal one day, very young, about your guys' age, maybe younger. And I get in the airplane, and there's only like 5 people in the plane. It's a 707, by the way. Boeing 707. 707. Right. We take off, and the pilot just pulls the plane up, and we're like, whoa, going up. Everybody know what the noise abatement program is in Orange County? Now, Orange County's flight path is directly over Newport Beach.
Yeah.
And back in the 70s, the Newport Beach residents, them being those folks, said, we don't like that noise. Shut the airport down. I said, well, hell no.
That's what happened.
And they said, but you guys have to do something. So we're going to come up with a noise abatement program, which means that as the pilots are going over Newport Beach, they reduce the power and they float. Now, in order to do that, you have to climb real fast over Costa Mesa. I mean, real fast. Get up high enough, shut the power off, and float. And when you go and float, you end up somewhere over the ocean. And then they say, okay, we're past Newport, hit the jet, and then they take off again, right? So this is what happens to me. I'm like,
Oh gosh.
ah! He turns the power off, and you hear the engines physically just take off. Right? Now, some of you have gone to the Tower of Horror at Disneyland, right? And you know that feeling when they let down?
Oh, yeah.
That's what happened to me. Ah! We're going to fall down into Newport. And the stewardess, being the kind of lady she is, she goes, oh, honey, don't worry. It's what we do now. I'm like, you do, not me. Okay? She goes, it's the noise abatement program. And I'm thinking, noise what? Who the hell cares? And so she's strapped, I'm strapped in, and we're going down, and all of a sudden the pilot hits the jets. It's the best feeling in the world. I'm like, oh, okay. So she comes back. She says, are you 21? No. She goes, and this is back in the days when they didn't really care.
Yeah, I know.
So that's how I remember it. That's the story. All right. Long story for a sign. Okay. Now, what else do we have? These are called gauge blocks. They're all calibrated. There's different sizes all over the place. Various things, giant parallels. These are our standards, right? And we didn't find out what the sign was. So 5 times the sine of 707 is what? Believe it. 3.535. I know it by 3535, right? 3.535. So I would have to get this at 535. So I'm going to get, for that, I'm going to get a 135 block. And I'm going to get a 400 block. And when I rub the 400 with the 135, what do I get?
Connection.
535. That's 3" 535. So now I just need a 30" block, and I rub them all together.
I need the book.
And I need to make sure they stick together, by the way. Okay. And now when I go like that, this should be 45. And if I go like that, that should be 45. Now let's check this to see if it's good. And I'm going to put this over here to make sure that it doesn't drop over. Okay. And I'm just going to adjust this accordingly. Be real close. And I'm going to go over here. I'm going to zero that bad boy out. I want to run her across. Oh my gosh! And this is not good. And as you can see, it's about 20 thousandths off. Okay, it's a lot. So this is not a good standard. So I don't know. I don't know how I got in there. So let's check another one. Now I gotta redeem myself here. I don't have another one, do I? I remember this one. Oh boy. Let's check this one. This one's a kind of a bigger one. Let's see if that's good. And again, you always want to make sure your setup is, tight. Okay. Do this one here. Let's check this out. This one's probably worse, to tell you the truth. It's probably been banged around.
It's like my math.
Okay, I got 0 there. Just gonna hold that. It's 0 there and it doesn't even go on here. Okay, let's see what I got. Yeah, this one's even worse. This is 30 thousandths off.
Wow.
Okay?
Wanna check mine that I made?
Yeah, let's check yours.
So what not to have?
Right?
You didn't get an A on this one, did you?
I don't remember. You know what?
Yeah, you didn't.
I didn't.
No.
Wow. There's someone in the
So
box.
let's see.
Oh my gosh.
I could already tell you right now it's on.
Oh, moment of truth. Whoa.
Whoa.
Yeah.
You know, it's been nicked up and banged up and
Yep.
back.
So
Yup.
it's maybe not quite right. But okay. It is what it is. We've checked the 30 degrees and we've checked this one, so we're going to give you back this one. But we'll check it again. It could be that I want to make sure. There you go. I got 14, 135. Yep.
Now they're all.
Now that's all banged up, right? All right, put this back. Now when you put it back, there's a little chamois cloth. Just make sure you get the oil off. Your oil on your hands makes things rust. If you haven't figured that out yet, you should have figured it out by now, because if you handled your part, you'll notice there's rust on it. That's because of the oil on your hands. So when you put it back, just make sure you wipe it off with your little chamois cloth. Well, you guys want to know why it's off?
Right, in the wrong spot.
The wrong one.
Yeah. I picked 115 instead of 135. That's why they're off.
Triangle's good.
So the instructors
Yeah,
do it.
yeah.
All right.
Machine.
Now,
Hey, for sure.
these are the same thing. They're called hope blocks.
Hope.
Hope. Same thing. They're standards. Okay, and these are donated, so they're not really. I mean, they're supposed to put together, and then what they do after they put them together, they have a hole for them, and they can put something together to hold them, so it's always there. Okay. Let's see what else we got here. Check over here, the micrometers. So remember, I told you there's oil sizes of micrometers, right? So 5 to 6. Just measures 1 inch from 5 inch to 6 inch. That's all it's designed for, right? And they make them all the way up to like 30 inches. Okay, so that's pretty cool. Let's see what else we got here. Okay, So this is what we call a depth mic. A depth mic. A depth mic. And it's a 0 to 1 depth mic. And as you can see, as I turn it, it goes down. It's going to be flush when I get to 0. Okay, see that? Flush. And the way you check it is by simply putting it down like this and making sure you push down hard, and it should pretty much zero out. Okay? Pretty much zero out. Okay? Now these are kind of difficult to read in that you need to read what's covered. So if I turn this exactly to 100 thousandths, that's what it looks like. 100 thousandths. Notice that the thing is sticking out 100 thousandths. See that?
These things read like backwards, don't they?
It does.
Yeah, I know when
It
you first
reads
start
what's
class.
covered.
Yeah.
Okay? Now I'm going to move it to 200 thousandths so you can actually see it. Okay? Okay? That's 100, and that's how much this is sticking out right here. Now I'm going to move it to 200. And now that is 200. See that? 200. You'll notice that the 100 is covered. See that? It's 200. And you'll notice the 100 is covered. So you got to read what's covered first. So if you can see the 3, it's not 3 yet. No. I can't see the 1, so it's got to at least be 1. And I can see the 2, and it's on the 0. Or that it reads the same way as a regular mic, but backwards. Okay?
Are we going to be using that in class? No.
Well, we can use it like if I want to check how deep this hole is, you know, I could just go like this, and I could say, well, let's see. This hole is 493 thousandths. I'm going to show you what that looks like. 493. 493. 493. 493. Let's see. Well, it looks like it's right close to the 5, George. Not quite past the 5.
No.
Would that read or 4? No, it would be 475 plus the, right?
475 plus whatever you're reading.
Right.
Because I can't see the 4, and I can't see the 3 lines after the 4, can I?
482.
493.
493.
Okay. All right. Now, these come with different rods. So you can just take the rod off. Like so. And now, we put the rod in, and now it's instantly become a 1 to 2 depth micrometer. See it? And it goes all the way up to 3 inch. Okay.
Has there been any modern upgrades since making that solves that issue, or they've just kind of let it lie the way it is?
You mean what issue?
I mean, as far as reading it, having to read it backwards and it covering it, has anybody tried to adjust that? Like,
Yeah. They got digital mic.
Well, yeah, digital,
Yeah.
of course, but like in
And that's the way they do it. They have a
Yeah.
digital mic, and they have the regular. They have this, and they have a digital portion.
I see.
So you get the best of both worlds, right?
Got it.
Now, for me, I don't know. I don't. You can't read it, then
Right.
don't use it.
It's a good,
Good advice.
yeah.
All right. Let's see what else we got. Dial indicators. We've got all different types of dial indicators. So there's one. As you can see, it's a dial indicator. Yeah. And the good thing about dial indicators is when you read, and this has got the face that's come off, that's why it's like that. But other than that, it's pretty nice. You'll notice that there's a big face, big, nice face, right? And that's all nice, okay? It's all nice. And how to read that face? Because you always go, how does this read? Well, right in the middle, usually, there's a number, and this one says 0.005. See that? 0.005? That's a half a thousandths, half of 1. 0.001 divided in 2 is 0.005. Okay? Half a thou. That means each line on that dial face is a half a thou. So it makes it real easy to, that's 10 thousandths right there. That's 5.5. You can really get really close with this. Okay. Then they have others that read it reads in, this one reads in thousands, no big deal. Let's go over here and get this one, because we can compare this one to this. I'm going to put this over here, put these two side by side so you can see the difference. So the nice thing about this is that if I have an inspection to do, and I know that I have a standard here, and just let's make it a real standard. Let's put this over here, and I said this is going to be, what did we say, 2 inches, right? Right. So let's check the 2-inch block. So I'm going to adjust this so that it is on 0 at 2 inches. Okay, that's my standard. So now let's see if it's exactly 2 inches. Right on the money. Right on the money. And so let's say you had thousands of these things. Thousands of them. You go, oh man, it's going to take me forever with a micrometer. Oh, that one's okay. Let's check the next one. Check that one. That one's okay too. Okay, you go real quick, huh? All you gotta do is check to see if it's on 0. Okay, now, this one reads in thousandths. This one reads in tenths of thousandths. And you go, huh? Tenths of thousandths? That's right. That means it divides 1,000 into 10 more, 0.0001, right? And I'm going to just put this down. I'm going to adjust this accordingly. I'm going to tighten the top one, and there's two knobs here. The top one tightens it, and you leave the bottom one loose, and then you have a little screw over here which can bring it down easily. Oh, here we go. One second. George. Can I go down a little more? All right, there we go. I think this, oh, I know what's, I know what's going on. The screw is come loose. Not used a whole lot. There we go. All right, so we got that. And I'm going to come down like this, look a little bit more. Oh man, this thing is really, it's broken a little bit. It needs to be screwed in. It's like somebody's jacked this thing a little bit. All right, we'll just bring it up like this. And look at that. Oh my gosh. Yeah, I don't know, it might be stripped. All right, sometimes it doesn't cooperate, but we'll make it cooperate. All right. Now it's like that. We've tightened both of them. And if I have... All right.
Take your time.
Yeah, I know. It's okay, George. You're on camera. Okay, good. All right, here we go. Do it like that. Let's get,
Everything's
One thing after another here. All right, here we go. It looks like somebody messed
Dropped
with
it?
this. No, they messed with it. I don't know. Sometimes people mess with things and they shouldn't be messing with them. And it's just, because I know that I had it adjusted last semester. There we go.
This being intense though should give you a closer reading than the one.
Exactly.
that's 1,000.
So I have it set to exactly a 2-inch standard here. And so now I can measure these to a tenth. Because I got that zeroed. Yeah, I'm 1/10 smaller. 1/10 smaller. Which is acceptable. Okay? 1/10 smaller. And I can actually check my parallelism from one end to another. And over here, it's smaller. And when I slide it all the way over here, it's right on zero. So I'm 1/10 smaller on the skinny end, and on the fat end, I'm right on the money. So I'm not the size, and I'm not parallel by 1/10. And you all go, oh man, what piece of junk, right?
Scrap it.
You will appreciate when you can do that every time, okay? All right. That's how you check things. Fairness, swears, and fun. So, okay. 1, 2, 3 blocks. What else do we have? I go through these things like this sometimes, just to show people what we have. Over here, we have a bunch of threading stuff. We have what we call go and no-go gauges. Go, no-go, right? So this one happens to be a 3/4 16 go gauge. So if I make a thread on a lathe and I put this on and it fits, then it's a go. I have another one over here, which is a 3/16. Well, George. Yeah, here it is. It's a 3/16 no-go. No-go. So this one should fit and this one should not fit. That's made for people that don't know how to read pitch micrometers. Okay? Because pitch diameters are how we measure threads, external threads.
Or again, if you have like a lot of parts to check.
Yeah, if you have a lot of parts, this is what you use. And then if you're trying to figure out how many threads per inch you have, we have something called a thread pitch gauge, which I'll open this up so you can see. What? And you have all these different pitches over here. Yeah. And you can just put that directly on the thread, and it'll tell you how many threads per inch there are. Okay. So, thread pitch gauge. And you're going to use this when you get my 102 class. Because you're going to make a thread. You're going to make a couple of threads, right? Right. All right. And then we have something called three-wire method. Three-wire method. That's to measure the outside diameter, I should say the pitch diameter, to find out if your thread's okay. Now, I'm not going to go over this because this is something you would learn 102. But basically, you've got 3 wires. And if you put 3 wires over the threads, 2 on the top, 1 on the bottom, and you measure over the wires, you get a measurement. That measurement is going to tell you whether it's within nominal size. Okay? And the reason they came up with that is because thread pitch mics cost about $300 a pop. $300 a pop, and you got to buy a pitch mic for every 4 threads. That becomes a lot of money. Okay, so nobody can afford that. The wires, $30. You can do everything from the smallest to very large threads, depending on how much you want. Now here is another. Boy, this is real sticky. Stare it, and as you can see, it has the range on the right, on your right side, and on the opposite side, it has the increment. The range and the increment. The range and the increment over here. The range and the increment over here. How many zeros is that? 3, isn't it? And 1 after it. That means each line on that dial face, range and increment, each line on that dial face is 1/10 of 1 thousandth. Range. Okay. So that means that this one is just like this one here. It's very sensitive. And it's really sticky. I mean, really sticky. We got this donated this summer by a guy, and he's retiring. And he said, I bought a bunch of gauges. I'm going to throw them in the trash. You want them? And I looked at him and I said, yeah, I want them. Of course I want them. You're not going to throw this in the trash, are you? He goes, oh. And a little bit of fluid in there, a little bit of sterile oil, a little cleaning.
How old do you think that gauge is?
This,
As a sign of like, you know, you get what you pay for because the stare stuff is cool.
that sterile I can tell you from 1950.
Right? So I like the yellow.
So it was made in the USA, you bet.
Back then.
Is
yeah.
it still good? Yep. Well, guarantee it's probably still good. Needs a little cleaning, but it's still good. I trust it over anything I buy offshore.
Right,
Okay. Okay. Any questions on this stuff, right?
I have a
Yes.
question. So on the syllabus that you gave us, there's decent details about like what we just talked about right now.
There's some.
Okay.
There's some. Now we have other gauges over here. And these, anybody want to guess what these are? What are those? What are those?
Those
Radius.
Radius gauges. I want to check the radius of something. Let's say I want to check the radius over here, this part, and I could put this little radius gauge in here and say, well, let's see if that fits in there. Oh, it don't fit in there. So it's not a 1/4 inch radius, right? So you'd have to go in and you'd have to try to figure out. Let's see, is it this one? Hey, that looks pretty good. That looks real good. It's a 3/16 radius. Okay, so it's a visual gauge, right? And then you have these little doo-hops over here. And this is called a telescoping gauge. A telescoping gauge. Why is it a telescoping gauge? Because if I have a hole, that's about, I don't know, 3 inches or so. Let's get my little ruler out. Of about 3.5 inches. You say, well, how am I going to measure that hole diameter of 3.5 inches? Well, you can get your calipers out, right? But you say, you know, I need to go way deep inside the hole. And my calipers don't fit inside that hole. Well, you would go like this, and you would push this in, just like that. Put it inside the hole. And then you would turn this little knob here, okay? And just slightly. And what would happen is you'd hold it at an angle like that, and your hole's here, like that, and you just move it like this, past center, and then take it out. What's the shortest distance between 2 points? Straight line. If you're at an angle, your line's longer, is it not? As you go past center on your circle, the shortest distance will be the distance from one point on the hole to the opposite point. Everything else will get bigger as you go lengthwise. So then you take it out, and because you've got this little break on here, it squeezes it down. Then you just take a regular mic and mic over this, and it tells you exactly how big the hole is. And they got big sets on this. They got sets that these different sets like this over here come in all different sets. See that? All different steps, all the way from the little bitty ones to the Well, this is not a complete set, but somebody put them in the air somewhere. But yeah, from this one goes from 1/2 inch all the way to 3.5 inch. Yeah. No, excuse me, to 6 inch. 6 inch. Alrighty, let's see, that's telescoping gauges. What else we got here? You guys already know what a surface roughness gauge is like, right? Because all of you had to check it, right? Surface roughness gauge. All right. Let's see what this. Check this. Whoa. Oh. Oh. This is like. I hate when we do this, but. I'm gonna hold that like that. But, let's see. This is what we call a dial bore gauge. And of course it's been taken all apart and Okay, so a dial bore gauge is meant to measure intents. So this is how you measure a hole diameter very, very accurately. Intents. Okay. The telescoping gauges is accurate to 1/1000th of an inch. This is accurate to 1/10 of 1/1000th of an inch. Okay. Now, dial bore gauges cost a lot of money. A set like this costs easily $800. Okay. So you got to set it first with a standard that you know is that. Then once you have that, then you go and you measure your hole accordingly. Okay. So it's a little bit of work to do, but it's very, very precise. Very precise. And I can see somebody's messed around with this a little bit. I'm going to put it back. I'm going to take very good care here and make sure I don't ding it. Okay. Any questions on what you've seen so far?
What's that thing?
What's that thing? It's an optical comparator. Okay, so some of you have seen shadow boxes before. You know, you went to the movies and you put your hands up, right? All right, that's a shadow box. Same thing. Okay, it shines a light from a mirror. Actually, the way it works, you can see this. It's very easy. It's going to shine a light from here. It's going to shine it across over here to this lens. In the back of that lens is a mirror at a 45-degree angle. That's going to reflect it onto this. Now the lens here and the lens here have magnifications to them. That's why when you see this, you say it's a little part, but over here it looks like really big. That's because it's been magnified, 10x in this particular case. Okay? So it's going to blow it up 10x. Some have 20, some have 30, some have 50x. And that's really big. Okay, that's like sometimes too big to work with because you're like, okay, I just need to find the hole, but the hole is like, okay, that's way too big for me, right? So I just need about this big, and I can find the hole, right? And then over here, no big deal. You just turn on everything, and over here you turn on everything, and it's got a DRO. That means when I move it like this, I can measure this way, and I can measure up and down. In and out is focused. I also can measure point to point. I can measure a line. I can measure a circle. I can measure a distance. I can measure an angle. I can adjust it so it's skew. And then there's some magic, and I don't know what that is, but we'll just say it's to find an unknown point, okay? But point-to-point, line, circle, and then angle are all about what you need to know. Because that's what you want to know. You want to know the distance, you want to know the angle, and you want to know circles and radiuses. And if you can do all that with this, you're okay. The rest of the stuff you can read the manual about and say, oh, you can also do this, this, and this. That's great. You can also calculate points. I find that if you rely too much on machines like this to do stuff like that, sometimes there's a difference between this and what the actual hard measurement is. So then it becomes a question of, was this perfectly in focus? And if it's not, then your answer's not. Okay? So hard measurements like CMMs and whatnot are really good. However, the technology of non-touch measurement is becoming more and more precise. There's a big difference between this accuracy of this machine and that Keyence machine that's in the tool crib that you see sitting on the desk. That's a $60,000 machine. It's accurate to 8 millionths. Yeah, 0.00008. 8 millionths, and it can go even further if you want to pay for the extra. Okay, but 8 millionths for around here, well, we're good. Guys, is 8 millionths okay? Yeah, it's okay with me. If we get even close to that, we're fine. Because 90% of the work that we're going to do in this class, in any of our classes, will probably not be past 1/10 of a thousandth. Okay? Now, when you get out in the industry, sometimes you got to split hairs. And that's for splitting hairs. Okay? And you can learn about that when you get into your metrology class, and I'll show you a little bit when I get into my 102, 103 classes. I'll show you guys how to use it a little bit. Okay? It's not a big deal. It's pretty easy. It's actually pretty easy to use. And there's some programming with it, but you can do one-offs, and it's really fast, quick. It's really accurate too.
60 grand.
All right. So, Optical Comparator. What's this? Hardness Tester. And it's to measure the hardness of something. So if I want to check the hardness of something, I could use this machine. Now, why would you want to check the hardness of something? Well, because the hardness is how you determine whether a part has been hardened correctly. Let's see. There we go. Put this away very carefully. And I'm going to give you a little demo on that. Okay. All right. So, George, do you remember how to turn it on? See if that turns on. Son of a gun. Great. Turn on the switch and it turns on. Okay, we have something called a little standard. A little standard, and you have to check it with the standard first. Okay. Now this standard, you'll notice it has dots on one end, right? And that's where the impressions were taken. Yeah. See where the impressions were taken? Okay. On the opposite end, there should be no impressions. Now in this particular case, there was some student says, hey, looks like the top one's all used up. I think I'll use the bottom one. No good. No bueno. Okay? You don't do that because it's got to sit flush. If I'm sitting cockeyed like that, it's not going to have a good measurement. So I took a stone, tried to clean it up. It's all right. All righty. So now we put it over here. What you got to do? Alrighty. What you gotta do is you gotta pick a spot where it hasn't been used, which is this one's kind of hard to do. But we're gonna find it. There we go. Take my glasses off so I can see what I'm doing. you don't touch another hole that you've already done. Okay, hopefully that hasn't happened. So it says ready to test, Hardness Rockwell tester, scale C. There are about 5 or 6 scales. A, B, C, D, E, F. I mean, and probably more than that. In the machining business, we use 2 scales, C and B, okay? Typically speaking. B being the softer scale, C being the harder scale. Now on this one, it's pretty easy. You just go up, and it says ready to test. You go and you keep on turning, and it'll automatically do it yourself. Stop. It says measurement 33, hardness Rockwell 33. Now, you're going to verify this. What does it say on the side of that?
33.
33. That means that guess what? We're good. The measurement works because the machine is calibrated to what it's supposed to say. It does what it's supposed to do, okay? So we know that, and it's 33 on the C scale. And then I could take something else, I could take, a part and put it in there, and I could check the hardness of it if I wanted to after that. I don't have anything that's been hardened lately, so I'm not going to do it. But you would do the same thing. You would go ahead and check the hardness. Sorry about that. Hardness testing tool. Okay. Hardness testing tool. This one is the same thing. Let me just take that one out. We'll check this one. Okay. Go.
What's this little bit thing here for?
What's that little thing?
Yeah.
Well, you don't touch it first.
I don't planning to.
Don't even look at it, okay? This is for an adjustment that we don't do up here.
Doing it.
Don't go doing this to me, okay?
I don't know about electronics.
You see these screws right in here?
Yes.
For those, and I think there's one little adjustment in the back.
There is, yeah.
Okay. Don't mess with that. All right. Now this one is the manual one. This is what I grew up on. And a lot of people don't know how to use these things. And so, first thing, again, you gotta check, make sure that this bad boy is not on a spot. And you just simply turn it up. Alright, so somebody turn this for me. Very good, George. Okay. You just make sure this is going the right way here. So, we're gonna bring it down. See if it works. It's not working. It's sticky. All right. And I'm going to adjust it to 0. And bam. I'm going to let it go. It's going to release. And you're going to watch the needle still moving. Okay. Now I don't know if this is going to be a very good measurement or not, but we'll see. And you wait until the needle stops. You come back. And sure enough, it's not a good measurement. It says it's 55 Rockwell. So I know that's not good. And that's probably because I may have been, this thing is, it's not working. Somebody, I wonder if somebody messed with it because it was working the other day. Anyway, you bring it up to the dot over here. When it's loaded, you unload. It goes and stops. Bring it back to load, and you'll read it. I'll have to check this out. I didn't want that to happen. People come in here and start messing with dials, and it's not a good thing, right? It's just like a car, right? Start messing with all the stuff. And these machines are really sensitive. You start messing with it, and it's just really bad. I'm going to check the weights behind here, make sure it's the right weights, but there's a reason why it's not working. It was working this summer, which is what we do with this. All right, what else do we have? Now, what are these machines back here? You'll notice they are CMM machines, coordinate measuring machines, very precise measurement machines. And we also have over here, and you learn how to use these in the Metrology 180 class, or Metrology 180 class. And then over here, you have a roller arm. Yeah, roller arm. Yeah. And I can actually, oh, thank you. I can actually take measurements with my roller arm, and this will take as precise a measurement as your calipers or your micrometers, and even more. And I can go anywhere I want. I can take measurements over here. I can take measurements over here. They make these things that are so big that they can have an aircraft in here, and I can take a measurement over there, and I can take a measurement over there in the room, and it will measure the room, or measure the part in the aircraft in this room. Okay? So, very precise, very, very sensitive machine.
How much is that one?
These are $60,000 a piece. Yeah. And if you bang them around, you gotta replace them. So we bought 12 of them at this college. We got, or, yeah, 12.
How many you got left?
Yeah, 2 broken.
Oh, jeez.
We've only had them 4 years. So,
Don't even look at something.
don't look at me, because I don't touch them. Okay? Other than doing that. That one works still. So, be careful. That's all I gotta say. We got good equipment. That is state of the art. That technology is probably 5 years old. If you can run a machine like that, program it, I guarantee you we get you a job somewhere making a lot of money. I guarantee you that. Hexagon, who sells this, says, you have any graduates yet who can run these machines? Well, I've got a couple. Well, tell them to come talk to me, because I got a job for them. The guy who sold the machines, he'll hire them on the spot if he can run it.
So they got these machines with no operators out there, basically.
Yeah. I mean, what they do is they'll hire you, and then they'll send you to their school, and then they'll train you. But Brooke trains a lot of people that have them already in the companies. So what does she do? She uses their training program and our stuff in addition to train our people. And we use their simulations and their programs. And so once you learn how to use it, you're set to go out there.
What work specifically are they using things like that in aerospace?
Aerospace,
Yeah,
right. I mean, this is not the mom and pop shop.
Right.
Okay, you're not gonna find this at, ABC machining. It's just not, you're gonna look at that and go, I can't afford $60,000 for a arm that might be broken by accident, So, these are, this arm like that, SpaceX would use them. Anybody that's in the aerospace business, Parker Hannifin, Boeing, even medical device manufacturers that have small parts would use this. They are especially handy. They have them located right next to the machine, the CNC machine. So what's nice about this is that you can inspect the part, right? And all you're doing is shoot with it. And that information is going somewhere else, right, into a database.
Right.
And so it automatically, somebody could be in the inspection room looking at your parts and never have a part come off the machine. They're being inspected right on the machine, right? So that's the nice thing. You're eliminating that setup time, the downtime, and instead of having to take the part off and go to the next cycle, you actually continue onward, right? And you eliminate all the, I think it measures 500,000. So I think it measures 502. Well, I think it measures 503. You eliminate that entirely, because that's the standard, right?
That's big because that's a whole department in some
Right.
companies.
You could actually, if you do it right, those machines could probably replace 50%, maybe even more of the inspectors out there.
Right.
But you have to have inspectors that are willing to know this, right?
Right.
And you shouldn't look at it that way. You should look at it as, I can do 50% more work now. right? Because now, instead of being limited by my inspection, I can take on, buy more machines and hire more machinists, and I can keep the people that have my inspection and just bring them up to where each one is now responsible for vastly more stuff. Instead of one inspector, 2 machines, or 3 machines, or 4 machines, I can have one inspector go 10 machines, no problem, maybe 15. Now I can fill my shop up with 150 machines and I can keep all my inspectors, right? That's the way to look at it. And if people think about that, it becomes totally different, right? So offshore manufacturing thinks that way. They don't think, oh, how am I going to cut heads? No, they think of how am I going to get more room out of my shop and put more machines that way, right? Or how am I going to go that way and get more machines? How am I going to go that way and make more machines? That's what they think of, and that's the way we need to start thinking here. Because if we start thinking that way, then we become a powerhouse in manufacturing. We can, and we've done it. If you guys don't think so, start reading your books about the history of how aircraft was made during World War II. Okay? Just think about that. We went from 0. We didn't know how to make airplanes. Japan knew how to make airplanes better than we did at the beginning. France knew how to make airplanes. France! The Germans. The English even knew how to make airplanes better than we did. At the end of the war, anybody know how many aircraft or planes we were pumping out per day?
Ridiculous amount.
20,000.
Yeah, well, you know, there was a figure of 50,000 a day at the end of the war, and they shut it down. They shut it down actually in 1944. We're running out of room to store these things, you know? Honest to God. So we learned how to make it real fast, and we made really good aircraft. Maybe not really good, but aircraft that was good enough. And then came the jet age, right? And then we figured out how to make jet engines, and then we go, oh, put a jet engine on there, right? So now that's where we're at, and we have that ability to do that here. All the tools that you see in this machine shop, all of it, is stuff that simulates what we can do out there in manufacturing. Not only for aerospace, not only for aircraft, everything. For marine manufacturing, auto manufacturing, you know, refrigerator manufacturing, any kind of manufacturing. This all begins right here. This is where it starts, okay? Anything that you look at, that cup, I'm gonna grab this cup. This is my cup, right?
I think so.
So you look at a cup and you go, what the hell does a cup have to do with manufacturing, right? You know, they hire some guy to make this cup, right? No. Now they got a die. Cuts the paper, comes up, curls those edges, glues that seam in there, puts that bottom in there. It's all done with, yeah, some guy made it on a mill lathe, right? You think about it. That's how this is made. You go look at the machine that makes it. It's not made out of paper mache, okay? It's made out of pure steel. Everything, right? Anything you touch today, think about that. That cell phone. I was not some guy that thought, I glue a bunch of keys together. Right? It's cut and paste, right? No. Made out of machines. The car you get into, the tennis shoes you wear. When you sit at the table, think about how the chair was made. Right? Think about all those things. Think about a pair of scissors. Think about the toothpaste jar, right? Or the toothpaste tube that you're going to use. How was that made?
Some guy sitting
Yeah, you know, some guy he sat there and he wrapped a piece of plastic around and then no, that was all done via machine, okay? When you guys go out and see, I mean, there is a number of things that you guys can look out there and you can say, wow, that's cool. I made, I was going to go work in Chicago, and it was a plant that I was supposed to go to. I didn't end up going, but we made sterile water. You go, sterile water? How do you make sterile water? Well, you sterilize the water, right? But then you got to bag it. And you think, no problem. Just give me a bag and fill it up. And then we'll seal it with a Ziploc that and we'll just give it to somebody. Oh, it can't be that way, right? Can't do it that way. Although, you think about it, well, maybe that is a good way, right? But no, they have a machine. And you say, well, how do we cut down the cost? Well, guess what? We have them in a bottle. Yeah, in a bottle. Now think about your Pepsi bottle, or your Coca-Cola bottle, or your big plastic bottle, and think about how that is made. And they have this little machine, it's called an extruder, and it extrudes out what they call a parison. And it's all it is a tube of plastic that gets squeezed out. Okay? So I want you to think of a tube, just like this, it's squeezed out. And then they have a die over here, it comes down, and it squeezes it in the shape, and it closes it off. Now, the top over here is where the plastic comes out, but in the middle is a faucet. And it fills it with whatever, Coca-Cola, sterile water, yeah, whatever. And it fills it, and it has a little eye, and says, okay, that's enough. And then there's another die that comes up at the top and closes it. And not only closes it, but it cuts it off too. And then both of them open, and the bag drops down to the bottom. That's how they do it. Now, why is that? Why does it drop to the bottom? It does two things. One, it determines whether that bag is thick enough and has been sealed enough so that it doesn't break. And if it has the drop test built into it, I've done my inspection of a drop test with that bag. So now there's an operator down there picking up the bag, checking to make sure it doesn't leak. You can tell if it leaks right off. It's like, dropping a water balloon on the floor, right? You can tell. So now you put them in backs, and it just keeps on going all day long. Okay? Produced them 7 days a week, 24 hours a day. George, come out here and help us with this machine stuff, man. Now, my job was to design and implement a new bottle thing for them. I did that, but it took a long time, and I was going to go live there. But they said, hey, we're going to send you down to Mexico, and you can run the show up down there. And I said, no, not doing that. No. No offense to anybody, no. Okay. So that's how I lost that job. Okay. All right. Any questions? It's a little story of my life. All right.
Interesting facts.
Well, it's the way it's done. All right, guys, let's get back to work.